Hey everyone, welcome. In this video, I'm going to show you how TCP/IP works. So, to better understand TCP/IP, we'll start our exploration based on the OSI model and then compare it to the TCP/IP model. I'm super excited to show you the magic of networking. If you're interested, stay with us till the end and enjoy understanding how the network works. You may know that we had two networking models, OSI and TCP/IP. TCP/IP won the battle by the end of the 1990s and became the common choice as the only networking model. Since then, we use the TCP/IP model everywhere. So, you may ask, okay, then why do you want to start with OSI? Well, the answer is straightforward. That is because the OSI model is still relevant and widely used as a conceptual framework for understanding network protocols and communication. While the TCP/IP model has become the dominant and practical standard for Internet communication, the OSI model continues to persist in educational settings, discussions, in certain industries. If you want to know more about the basics and history of networking models, you can watch our previous videos in this playlist. Let's get started. The OSI model consists of 7 layers, each explaining a specific aspect of network communications. The first step is to memorize their names and functionalities. I will explain their functionalities in 2 ways. First, with a simple and brief overview of each layer, and then by examining them in a real and practical context. Application layer, the 7th layer. This layer serves as the direct interface with network-aware applications, referring to the applications that operate on the network. You might wonder what we mean by network-aware applications. The answer is simple. These are applications that require network communication to function. Examples include web browsers, email clients, video streaming apps, voice-over IP services, file sharing applications, online gaming platforms, collaboration tools, remote desktop applications, and various other that might come to mind. These layers enable these applications to access network resources. Importantly, it defines the services these applications need, such as HTTP, SMTP, FTP, and so on, rather than the application themselves. Presentation layer, the 6th layer. This layer is responsible for encoding data being sent and received between devices. For example, a web browser receives data in HTML format or a picture in JPG, which are popular and widely understandable standards. Session layer, the 5th layer. This layer is responsible for initiating, terminating, and managing communication between devices. Transport layer, the 4th layer. This layer is in charge of establishing reliable communication and the separation and segregation of application functionalities. For example, imagine you are surfing the web using a web browser and listening to an online podcast at the same time. This layer should ensure that the correct data is received by the related application. Additionally, This layer is responsible for ensuring that the speed of sending and receiving data is the same between devices on both sides, which is known as flow control. Another responsibility of this layer is ensuring that the data is not corrupted, which is called data integrity. The two primary protocols in this layer are the Transmission Control Protocol, or TCP, and the User Datagram Protocol, or UDP. These protocols provide different mechanisms for reliable and unreliable communication, respectively. Transmission Control Protocol, or TCP. TCP is a connection-oriented and reliable transport protocol. It ensures the reliable delivery of data by establishing a connection between devices, providing error checking, flow control, and retransmission of lost packets. TCP is commonly used for applications that require reliable and ordered data delivery, such as web browsing, email, and file transfers. User Datagram Protocol, or UDP. UDP is a connectionless and unreliable transport protocol. It does not establish a connection before sending data and does not guarantee the delivery of packets. While UDP lacks some of the reliability features of TCP, it is faster and more suitable for applications where occasional packet loss is acceptable. UDP is commonly used for real-time applications like video streaming, online gaming, and voice over IP or VoIP. Network layer, the third layer. This layer is responsible for logical addressing used between source and destination devices for end-to-end communication. Additionally, this layer is in charge of routing packets between source and destination. One of the widely known protocols of this layer is IP. Data link layer, the second layer. This layer is responsible for physical addressing used for communication between devices. Additionally, it allows devices connected to the same network segment to communicate and is in charge of error detection. Lastly, physical layer, the first layer. This layer introduces physical standards used in network communications. Now that you have a basic understanding of the OSI layers, let's illustrate their practical application to better comprehend what occurs behind the scenes. In this example, we'll explore how two devices communicate over the network using the OSI model. Imagine you want to book a hotel for your vacation through their website. In the diagram, your device, whether it's a computer or a smartphone, it doesn't matter, is on the left side attempting to connect to the hotel's web server on the right side. At the bottom middle of the diagram, there are three routers representing network connectivity, specifically internet connectivity. On both sides, OSI layers are depicted. We will delve into what happens when you open your browser, navigate to the hotel website, make your booking, and exit the site. Through this exploration, we'll examine the OSI layers from the top down. And again, we started from layer 7. So, first step, layer 7, application layer. You start by opening your browser and typing the hotel website address. When you open the browser and enter the address, your browser doesn't communicate with the application layer until you hit the enter key. Okay? Once you press enter, your operating system recognizes the request received from your browser and forwards it to the lower layers. Second step, layer 6, presentation layer. The presentation layer's job is to receive user data from the application layer, such as the inputted website address, and convert its format into a universally understandable language between software or applications. What does that mean? Let me explain. Your device may have various browsers like Google Chrome, Firefox, Microsoft Edge, Safari, and others. On the other side, the hotel server may use one of multiple types of web servers like Microsoft IIS, IBM WebSphere, or Apache. With this diversity among applications, how can you be sure that your request is understandable for the hotel's server, considering the type of browsers and web server in use? No need to worry. Creating coordination between these applications is the task of the presentation layer. This layer converts the request format into a universally understandable format like HTML. Secures the established connection using popular methods and standards compatible with browsers. And finally, delivers the data to the lower layer. Third step, layer 5, or session layer. The role of this layer is very simple. It initiates, terminates, manages, and maintains the connection between two devices from the beginning to the end. At any moment, your device may establish multiple connections to other devices, or vice versa. In a large network with a high traffic, my friends, a server may receive hundreds, thousands, or even millions of connections at a moment. The session layer is responsible for managing these active connections. In this example, the request for the hotel's website address created by your device is one of these active connections. The initiation of this connection occurs when you hit the enter key after typing the hotel's website address, and connection must be maintained until you have completed your booking. Finally, the connection will end when you navigate to another website in the same page or close the current page. Fourth step, layer 4. Transport layer. If there were an award for the most crucial OSI layer, my friends, it would undoubtedly go to the transport layer. This layer performs two pivotal tasks. Firstly, it ensures reliable communication sessions. Secondly, it manages logical separation and segregation between applications functions, closely interacting with the session layer. When your request reaches the transport layer, your browser needs to decide whether to send this request reliably, ensuring the other side receive it, or unreliably. That's assuming the other side somehow received the request. It's important to note that the application determines how to establish a connection, and the user plays no role in it. The browser then uses protocols like HTTP or HTTPS to communicate with the web server. These protocols, known for their reliability, prompt the web server to send an acknowledgement, or ACK, or a receipt for each received packet. As mentioned earlier, establishing a reliable connection is the task of TCP. Now, that you're somewhat familiar with how to establish a reliable connection, you might wonder why some applications choose unreliable connections. Unreliable connections are useful for real-time applications like voice over IP or VoIP, video conferencing, online games, and so on. In such applications, you may lose some packets during communication. And in these cases, the lost packets aren't resent. The second job of the transport layer, my friends, is to logically separate applications functions. In the TCP/IP protocol suite, which we'll cover in upcoming videos, this task is accomplished using port numbers. When your browser sends a request to the hotel web server, it ensures that the related application on the other side receives the request, not other application such as, let's say, mail or a database. For this purpose, the browser sends its request to a specific port on the web server. For example, if you use HTTP, the default web server port is 80. And if you use HTTPS, the default web server port is 443. These ports are known as destination ports, guiding your requests to a specific server on the other side. At this point, your device and the hotel server, assuming it's run an Apache web server for managing the hosted website, understand that you want to communicate with the hotel's website based on the specified ports, HTTP or HTTPS, and not with other hosted applications on that server, such as mail or database. Let's complicate the scenario a bit. Suppose you're playing an online game on your device while simultaneously using a specific application. In this situation, your device receives multiple connections from multiple locations. The hotel web server and the online gaming server. Each communication has two sides. You send a request, and in return, you receive a response. Therefore, your browser needs to separate its function from other network applications like that gaming application on your device. In this case, your browser ensures which connections are received from the hotel's web server. And this is where the source port comes into play. When your browser establishes a connection, your device operating system provides it with a unique source port number. This source port number, along with your request, reaches the hotel's web server. And the web server responds to your request, referring to the source port number generated by your device. Fifth step, Layer 3, Network Layer. My friends, after your browser determines how to communicate, whether it's a reliable or unreliable, and assigns port numbers, it's time for logical addresses. In the realm of logical addressing, we refer to IP addresses, responsible for end-to-end communication between two devices. In IP addressing terminology, we typically have a source IP address, which determining where the data originates, and a destination IP address indicating where the data should be directed. To draw a comparison to driving, imagine you're traveling from north to south, but you have several stops in between. That's where the Layer 2 job comes into play. Sixth step, Layer 2 data link layer. After tagging your request with source and destination addresses in Layer 3, it moves to the data link layer. In this layer, it acquires physical addresses known as MAC addresses, specifically designed for Ethernet networks. Keep in mind that different Layer 2 addresses exist for various network types, a topic we'll delve into in upcoming videos. In our example, your device seeks communication with the hotel web server. However, this endeavor requires traversing multiple routers, illustrated in the diagram. Your device, as the initiator, designates the web server's IP address as the destination IP and its gateway router's MAC address as the destination MAC address. When a router receives the packet, it consults its routing table to ascertain the next destination, like router 2. As the packet progresses through routers, the source and destination MAC addresses evolves accordingly. This process repeats until the packet reaches its final destination. It means the hotel web server. It's crucial to note that our explanation assumes the use of Ethernet networks, my friends. For other network types, such as X25, frame relay, ATM, MPLS, and more, distinct Layer 2 addressing methods are employed. At the CCNA level, in-depth knowledge of these technologies is unnecessary, except for Ethernet and MPLS, which we'll explore in future videos. Okay, seventh step, Layer 1, or physical layer. This layer is responsible for translating data to the electrical or optical signals that are in the cables. In this example, at the moment you send your request, electrical signals formatted in a way that's compatible with Ethernet standards. Okay, my friends. If we want to compare the TCP/IP model or protocol suite with the OSI model, I should say that in the context of defining networking, they are similar. However, concerning the protocols used in each model, as mentioned before, TCP/IP has won the battle. Another thing worth mentioning is that in the TCP/IP model, the top 3 layers falls into one layer known as the application layer, because the functions of these layers are completed before the data of a certain network-aware application leaves the device itself. In this diagram, you can see the most popular protocols of TCP/IP that exist in both the TCP/IP and OSI models. Okay, now you understand how devices can communicate over the network. But this is not the end of the story. Actually, if you want to master networking, you should know that you must build your knowledge on these layers and explore them as much as you can. Say, okay, at that certain step, I have obtained the expected knowledge of CCNA level. And now I want to go further to the next levels and dig deeper into technologies, standards, protocols, and approaches that are defined under these layers. Let me give you an example. In future videos, we will cover a bunch of topics like IP addressing, VLANs, spanning tree, and so on. Each of these protocols and technologies is defined and standardized in different layers of TCP/IP. So, just by having a clear understanding of this model, you can find your way in the networking world. Great! With this discussion, we reach the end of this video. In the upcoming videos, we dig deeper into exciting networking world. So, if you found the information helpful, I encourage you to subscribe and hit the notification bell. This ensures you're in the loop for our future videos. Liking and sharing this video would be fantastic. It helps us reach more folks interested in these topics. Thanks a bunch for tuning in.